All right, well, welcome everybody to our online classroom session for Sierra Mountain Center Avalanche 1. This is the first year that we've done the online programs here. We started in the spring when we got shut down there. We've refined them, adapted, and we'll continue to adapt them as we go into next year. We're going to start running the in-field sessions now. I've corresponded a lot with other guide services, health department. We've looked at restrictions as regards ski areas, recreation. I believe we can go ahead and do the field sessions appropriately. We're going to be taking precautions, and we're going to be making sure that we stay within the guidelines and regulations. And we want everybody who's participating to stay safe. We want guides to stay safe, and I want to stay safe too. But we believe we can make things operate functionally and safely. We'll be sending out to people some of the guidelines that we have. Mono County has seen a fairly large increase in COVID. So we want to make sure we're doing what we can not to overload the local hospital and lead to any more problems. But that'll become more relevant as we get into the field sessions. So starting things off here. We are Sierra Mountain Center based in Bishop, lovely Bishop. And by way of introduction, I'm SP Parker. I've been living in this area for 40 years now, 1980, originally from the South, the very deep South, New Zealand, and came here to go climbing. Did first avalanche course in probably 1982 or so with Norm Wilson out of Tahoe, who was one of the great-grandfathers of avalanche research, evaluation, and mitigation in the US. And I learned a lot from Norm then. Unfortunately, Norm's no longer with us. I run Sierra Mountain Center, been teaching guides course, or avalanche courses, I should say, since the 1990s. Things have been refined a lot since then. And this is just the latest iteration, and we'll talk a little bit about that. We were running programs last year. This is Panorama Dome, or actually it's Mammoth area, Mammoth Rock area out of Mammoth last year. We had snow this time last year, and this is Rock Creek Canyon, where we were doing courses then. Certainly less snow this year. However, I've been out looking at the snowpack in the Mammoth area, and we do have enough up there to do avalanche courses now. A lot of people think that we need a lot of snow to do an avalanche course. You don't. The shallower the snowpack, generally, the more interesting it is, the more variability, the more going on in it. And as we'll talk about when we go through things today, a shallow snowpack is often a dangerous snowpack. And that's what we've got at the moment. We've got an extremely variable, very weak snowpack. And it leads one to think about what might happen if we get more snow on top of it. We'll talk as we go through about the human factor side of things. Right now, we got shut down in the spring. The backcountry skiing hasn't been great. There's an awful lot of people out there who are really antsy to get out in the snow. However, we've got to temper that enthusiasm because, as I said, we have a very weak snowpack at the moment. And if we get a foot, 2 feet of snow on top of this weak snowpack, it's going to be pretty interesting as to what goes on. And I could imagine that people might get caught in avalanches. So keep that in mind. We're going to talk about a lot of stuff today, but we have what I, as an avalanche practitioner, would call a very interesting snowpack. And hopefully we'll get to look at that as folks get out in the field more. So this is the Avalanche 1 course. The focus on this is decision making. We all want to go out and get into the backcountry and have fun. We need to make decisions about when it's good to go, when it's not. And to do that, we want to go ahead and create a framework in which to manage the risk. And we want a system rather than a haphazard, well, I don't know, what do you think? Well, I don't know, looks good to me. So that's what we're trying to get away from here. As part of it, people should have been able to get the manual. There's two different links here. We shortened the first one down there. People might have been able to get that via these links. If you haven't, jot down the link here, get to it later. If you have any problems, let me know. And the manual here is not a follow along with the presentation here. It's something to go ahead and look at a later date, no light bedtime reading, no middle of the night when you're tossing restlessly, something to pick up and read then. We're trying to get people different ways to look at stuff. We've got the handbook for people who are readers and learn that way and as a reference. We've got the outdoor session for people who want to listen and who want to do. This session is sort of those who prefer to listen. And they also go ahead and do things a little bit differently. So it's a number of different ways of coming to the same point. So AIARE online session. This link should have been sent out to folks. Okay, so let me close this out. There, so another way to look at things here. What we're doing is we're teaching an AIARE course, and AIARE is American Institute for Avalanche Research and Education. There's also the American Avalanche Association, also known as the AAA, and AAA has come up with what they want to see as outcomes from these courses. AIARE is a provider, just as Sierra Mountain Center is a provider. However, AIARE has taken it a step further, and they've developed materials that they disseminate to people such as ourselves, and we use their material and their framework to present these courses.
There's different stages of the AIARE progression, and there's a number of other providers out there who have similar progressions. AIARE is just one type of progression. You guys are in the one here, where we're going to learn a process. There's also the two, which is sort of coached application of that process in new situations. Between those two, you need the experience. Now, avalanche evaluation, mitigation is not a theoretical science. It's practical. You've got to get out there, do it, and we'll talk later about best ways to do it. As part of this one, AIARE 1, we're going to go ahead and we're going to cover avalanche rescue. Avalanche rescue is something that can take quite a long time to get proficient with and capable with. It's kind of like CPR. We need to know how to do it, but we really hope we're never going to have to use it. Our goal is to go through our backcountry career with never turning our beacon from transmit to receive in a real situation. We don't want to do that. We want to do everything we can avoid, or do to avoid that. If we have to do that for real, something has gone wrong. But we need to know how to do it because it's the backup to our decision making. We have to accept the fact that we don't know everything, and we can't evaluate everything, and we're probably going to make mistakes at some point, sometime, unfortunately.
So our rescue equipment and knowledge is to back up in case we make a mistake. When we get out in the field, we'll cover the basics of doing it. We don't have enough time to cover all the subtleties, ins and outs of it. That's where there's an additional one-day rescue program where we go much further into it. Generally, when we go out in the field, we're not going to go deep into avalanche terrain at all. We're by and large going to avoid it. We're going to look, we'll venture in when things are good. So we don't have to be super proficient with the equipment, but it's still something that we need to be able to provide to people to know how to use. So we'll give an abbreviated one during the field sessions. And hopefully you guys can get out with us or with somebody else and learn all the minutiae of it. Then you can go on to the level 2. One thing to think about here is that more knowledge doesn't necessarily make you safer if you forget all the basics. So we want to hammer on the basics, focus on that. Another way to look at this is that doing the AIARE 1 makes you part of a group, a contributor, and it's an introduction to identification and recognition of various factors. The AIARE 2 hopefully puts somebody into more of being a facilitator. We want to coach the application of decision-making. You're getting more into assessment and evaluation and managing that risk within your group. So they're two different things, and we'll talk later about the difference between the professional track and the recreational track. For our online here, we're going to have a morning session and an afternoon session. The morning session, we want to go ahead and look at the problems associated with avalanches. Then in the afternoon, we'll talk about how we're going to deal with those problems. Then when we get out in the field, hopefully people are managing to sign up for the field. It's taken us to now to figure out quite how we're going to do it. So if you haven't registered for field days, go ahead and get that on the calendar because they're getting busy, very busy, because we had to cancel the December programs. But we'll go out, we'll do the rescue, we'll look at terrain, we'll talk about selection, and we'll dig into the snow. Then on day 2, we'll try and put it all together on a day tour. So that's the general outline of what we want to do. So why do we want to do all this stuff? People die in avalanches. And we're doing recreation, we're out there having fun. We don't want to end up dying, but people do. Here's a graph over about 50 plus years, 55 years or more, probably 60 years of data. And you can see overall accident rates and fatalities are increasing. There was a dip once we get into about 2014 or so. I'm not sure of the why on that. Now remember, statistics can be misleading. There's more people in the backcountry now than there was in 1952. So yes, if the accident rate stays the same, we'd expect to see more fatalities. But overall, it is increasing. Looking at who gets caught here. Backcountry tourists and skiers are the biggest number. Again, same time period. Snowmobilers, however, right behind them. And this is more of a recent occurrence. The mortality rate amongst snowmobilers now is higher than amongst backcountry tourists. 20 years ago, you'd be lucky to get the snow, or 30 years, you'd be lucky to get the snow machine started, let alone get up into a start zone somewhere. So that's changed with the advent of much bigger, powerful machines, reliable, and they're relatively inexpensive. People can buy used ones fairly cheaply, especially around Mammoth at the moment. There's a huge number of snow machines. I was up there 10 days ago and they were everywhere on San Joaquin. And climbers are another group here. Most accidents to climbers are probably going to occur during the summer months rather than the winter. But climbers tend to be fairly oblivious of avalanche accidents. So I'm just looking for a book I've got here. Here we go. Some people might know Accidents in North American Mountaineering. This is the latest one of it. Probably hard to see there, but there's a tiny little dot on a climb in Canada called Polar Circus with a giant avalanche coming down inches away from the person. That triggered a whole section in this, avalanches and climbers. Climbers tend to be fairly oblivious of it, unfortunately. So they come in about third. Now, we've got side country here. Side country is generally what we also might refer to as lift access backcountry. These days, we try not to use the term side country. It kind of makes things feel a little less serious. In reality, once you go through the ski area boundary, through the gate, then you're in the backcountry. Ski patrol might be nearby, but as we'll talk about, a lot of having the people nearby doesn't mean a whole lot. With avalanche rescue, we have about a 30-minute maximum golden window to try and find somebody and get them out. After that, the rate of survival decreases. So if an accident happens, 30 minutes is going to get burned up very quickly. You've got 15 minutes to get back to ski patrol. They've got to get their act together. They've got to get to where the accident happened. They've got to get their equipment. So that 30 minutes is probably going to go. So very fast. Side country is just still backcountry. And we need to think about that if we're skiing, say, off June Mountain, where you can see the lift runs, but you're probably still hours from help. Inbounds riders. Mammoth Mountain, other ski areas do the best job they can of taking care of the hazard. However, they cannot eliminate it. And having an avalanche that occurs inbounds after ski patrol has done their control work is the sort of thing that keeps the ski patrol director lying awake late at night. It's the worst nightmare. But it happens, and it has happened on Mammoth Mountain. Nobody has died on Mammoth Mountain from the inbounds ones, but it has happened in other places around the country. So if I'm skiing Mammoth Mountain after a storm day, I'm going to wear a beacon. One of the first things patrol is going to do if something happens is turn on their beacons to search. Now, that's why they're waiting for other equipment, and they'll do that on the slight off chance that that person might be wearing a beacon. So I'll wear them, knowing that ski patrol does the best job they can. They're not infallible. So where do avalanches occur? Throughout the West, as we'd expect, Iowa, Kansas, Arkansas, those sort of places. Nope, not much going on there, not just in the snow. And so we get them in the West, we get them in the Far East, in the mountain states. When we look at this, we see that the majority of the accidents are in Colorado. And we'll talk about the why of that as we go through. Also, there's a fair number up in the mountain states of Idaho, Montana, Wyoming, even though the populations there are fairly small. California, with its large population, has less than those places. Again, we'll talk maybe about the reasons for that later. Alaska, not a lot of people up there, but a very high percentage of snow machine ownership. And again, snow machines now are some of the largest fatality group. So keep that in mind when you're traveling place to place. By month, as we'd expect, January, February, March are when most occur, but they can still occur in September, August, July. Again, those are going to be climbers out there. Looking at age groups here. Again, statistics can be a little misleading because there's not many people younger than 10 out in the backcountry. And as we get older, 60, there's fewer there. However, this is shifting and there are more older people getting caught in avalanches in the backcountry. Part of this is simply that older people are getting into the mountains more. People are taking this more as a lifetime avocation rather than something to do in your 20s. But the majority tend to be people, their 20s to early 30s. And this is not just restricted to avalanches. Now, if you can get through your 20s driving a car, that sort of thing, you're probably better off. It's a function of youth and the feeling of immortality. So, of course, there's nobody in that group out there at all, is there? I'm sure there isn't. The mean age here is about 30, even though in the last 10 years it's increasing to 32. For all victims in this study, it ranged from 6 years old to 67. But remember, this includes recreationalists, not only recreational people, but also people living in snow country. And that's probably where the very young come in. And there was an incident in Mammoth in the 1990s where a kid at the daycare center there was killed by a roof avalanche. It's still an avalanche. It's kind of in an urban environment, but people do die from roof avalanches. Looking at last year, there was 23 backcountry deaths and 4 inbound skiers there. Now on this one, we do see that the snowmobilers are the largest group, but we can put together skier and snowboarder together. They're both backcountry tourers, users there. So that was last year. Already this year, there's been a number of accidents. Last weekend, 3 people died in avalanches in Colorado, and I believe 1 up in Montana or Wyoming. So, people have already there have been fatalities already this year. And as I said, we have a very weak snowpack throughout the West, not just in the Sierra. So as we get more snow, people are going to need to be pretty careful when they go out there and temper that enthusiasm. So that's some data there for folks. So It's said that there's 5 different levels of learning. Now, where are you guys at? You're not in the bliss phase. No, you're here. No, maybe you're in the terror phase, which is okay. But we don't want terror to rule us. We want to go out there and make decisions that aren't based on terror. They're based upon assessment. However, we want to avoid the overconfidence phase. And again, it doesn't matter what we're doing. Overconfidence is bad news for us. I used to fly paragliders for a while. After 7 years, there's what's called the intermediate syndrome. It occurs in a lot of flying. People think they've seen it all and, yeah, I got this stuff figured out. It doesn't work that way at all. 7 years is sort of a trigger point for a lot of different things where we move into this overconfidence, complacent phase. So we've got to do everything we can not to get into that stage. And then hopefully, if you can get past that, you're in the expertise phase, and we'll talk more about what expertise really means as we get into some other factors. We'd all like to get to the wisdom phase. No, everybody right now is probably out there managing risk due to COVID. And there's a lot of similarities between how we manage our avalanche risk and our COVID risk. No stay-at-home orders, we'll stay away from the steeps. No, we've got an unseen danger. It's persistent. It's out there. We can reduce our exposure by social distancing or exposure to dangerous terrain. We can wear a mask, wear a beacon. We can be educated. We can choose who we do either activities with in either environment, by creating our own bubble, our own group. So I think there's been a lot of discussion about how people are used to managing avalanche risk, have found it fairly straightforward to start to manage the COVID risk because of the similarities. People who haven't had that risk management perspective have definitely had a harder time with it. I said, the terror phase that we just really don't want to stay in. Don't believe the bumper stickers that say no fear. Fear helps keep us alive, but it can't necessarily destroy us and have us holed up in a cave, afraid to do anything. We want to go out, we want to go ahead and respect the environment that we're in. We want to get out in it and get the rewards that make our lives better. However, we want to do that through a process. So rather than fear, I'd rather that people thought about respect for the environment that we're operating in. And according to Merriam-Webster, respect's an act of giving particular attention and consideration to. So we're considering the environment, we're respecting it, we're evaluating it, and we're making our decision based upon that. I'd also like to try and demystify this process as we go. There's a lot of stuff involved in making decisions in avalanche terrain. And it's easy for people to get bogged down with the complexities, the science, all the things going on. But in some ways, it's not that hard. As the avalanche danger goes up, the terrain we choose becomes simpler and less complex, less steep. As the danger decreases, we go ahead and can cautiously step it out into that complex, steeper terrain. As one goes up, the other goes down. So when we don't have questions, when we're not sure, we want to go ahead and back off. That's really what it comes down to. There's going to be times when you go into avalanche terrain, and there's going to be times when we don't. Our problem is figuring out which is which. We'll talk about using the avalanche report from the Avalanche Center, and that helps get away, as a starting point. It helps us get away from having to make all the decisions by ourselves. However, we also have to interpret it. So, there's a lot of big, steep ski descents in the Sierra Nevada, and people want to get out and do those. That's fine. However, for me, and certainly I think for most of us, as we get older, we're not going to predicate what we do in the backcountry upon the slope angle and how good it looks on Facebook and social media. I'm going to predicate it upon having a good time out there with family, friends, just being in the mountains and looking at it from that aspect. There's going to be on the steep descents and so on, there's going to be days or maybe even years when they're just not in condition. So our goal again is to figure out when things are in condition and when they're not. All right, so we'll start off here. As I said in the introduction, we're going to look at the problems first, then we'll look at some of the solutions. We'll define our terminology and we'll have some common ground to work with. So we can think of our danger here as a triangle. We've got weather, snowpack, and terrain. And there's a fourth one that we'll talk about later, but for now, we'll just go with these three. The first one we're going to look at is the snowpack. So now we get to start to use the chat box here. Let's go ahead, give me as many words for snow as you can think. Type them in there. No scientific terms. Give me what you've got for snow. Fluffy, dry, wet, heavy, dry, wet, cold, yep. Concrete, yep, we don't really want that one, do we? Cement, sticky, fun, okay, yep, loaded. Yeah. Sounds like what you get for a burrito. Mashed potatoes. Okay, so there's lots of different words that we have as backcountry users. Let's think about the best snow day of your life. What was the snow like? What was the weather that brought that type of snow? Type that on in there. Good snow, what was the weather that got to it? Light and fluffy, recent storm, cold and dry. Yep. No, everybody's kind of leaning towards the powder side of things. No, powder's not the only good snow that we get out there. No, give me something else that's good skiing, but not necessarily powder. Corn, okay. Wind buff, okay. What type of conditions, if anybody knows, leads to corn snow? Now that's really what the Sierra Nevada has best is corn snow. Spring, warm t-shirt, yep. So spring and warm for corn, what we want are warm days, cold nights, that sort of thing there. So let's go ahead and think now about the worst snow day of your life. What was the snow like? And what was the weather that led to that snow? I'm going to have to turn something off here, it sounds like. Okay. Thin cover, wet, slushy and hot, heavy, wet, windy, cold, wet, frozen. Hasn't been enough snow. Yep, that's certainly one at the moment, isn't it? So what we're looking for is to link between what we'll call good snow, what we'll call bad snow, and the weather that brings that type of snow. Now, we all know, we've been around enough, we know that snow falls to the ground at different times and in different weather conditions. Now, storm is just not a storm. Each storm has its own identity. We end up with a layered snowpack. When we look out and we just see snow, sometimes we fail to think about it being layered below the surface, and it is. We have layers, and between those layers, we have interfaces there. And it's these layers with different characteristics that give us potential layers of weakness that can lead to avalanches. So what we're going to define first off here is what we'll call a weak layer over a strong layer. which are loose snow avalanches, or we can have a strong layer over a weak layer, which we'll call slab avalanches. So that's our first two major distinctions, and we'll talk about that as we get into our different types of avalanches. But often when we're out there, we're looking for a weak layer, we're looking for a strong layer, we're seeing what the relationship between them is and what the interface between those two are as well. So we've got layers within the snowpack, and those layers are constantly undergoing change. And they're going to change at the surface and below the surface. So here we have some bear tracks in the snow. These were in the Sierra, I think out of Taboose Pass maybe. These are going to be buried. Everything we see at the surface is eventually buried. And that then is going to be potentially the interface between two layers. So another concept. When we're out there, we're going to be looking at the different types of snow at the surface. Then we think about how those layers are going to be buried. And there's variability at the surface, which is going to lead to variability below the surface as well. So as a broad category, we're going to say that there's two different types of effect: direct weather ones and indirect weather ones. Direct is what happens at the surface. So in the chat box here, let's go ahead and type in some of the things that affect the snow at the surface. What might some of those be? There's really 4 ones that we're looking for. Wind, yep. Sun. Rain, okay, we'll call that, maybe precipitation. Temperature, okay, yep, those are the main ones we've got there. Wind, temperature, radiation, what we're getting coming from the sun, which is similar to temperature, but not the same thing. Remember, we can have warm temperatures at night. Even when there's no sun, we've still got warm temperatures. Those warm temperatures are affecting the snowpack. And then precipitation, which can be more snow, it can be rain, it can be different types of snow. So again, everything we see is going to be buried. Then we have changes that occur within the snowpack. And these are what we're going to call indirect weather effects. And there's 2 factors here that we need to consider. It's going to be the temperature of the air and the height of the snow. So we're going to go ahead and get into a tiny bit of snow science here. It's not much, but I think we want it to enable us to understand what's going on as we go forward. Let's draw a graph here. We've got the height of the snow on one axis. We've got the temperature along this axis. Another concept to think about here and introduce. We, in this environment, have what we call seasonal snow. We get it in the winter, it melts off in the summer, as opposed to an Arctic or Antarctic climate where we have snow on the ground or ice on the ground all year round. During the summer, we've got solar radiation, warmth coming in. The ground absorbs that. In the winter, as the sun gets lower in the horizon, we're not getting that solar input and gain. The ground radiates and loses heat. If you go out and say, now, if you had a cold night up in Mammoth, you go outside, there's bare ground, the ground might be frozen. It's radiating energy away. Once we get snow on the ground, that acts as a blanket. Snow is a very good insulator. It holds air within its sort of crystal matrix, and air is a good insulator. We use that to our effect with our down jacket. It holds warmth or holds air in there. Air acts as insulation. So when we get snow on the ground, that insulates our ground. It can no longer radiate heat away, and it tends to stay at about 0 degrees centigrade, 32 Fahrenheit. Now we're talking with some science here, so let's use centigrade. So that's our first concept. If we didn't have that insulating blanket, the ground would freeze, plants would freeze, animals wouldn't be able to survive, and a lot of life would change if it wasn't for that basic fact. So our ground is at 0 degrees here. We're just going to call this point on our graph at 0. Let's have 50 centimeters of snow. Again, metric system, so no, we'll go with yay much. It looks a lot bigger on that, on my image there, but 50 centimeters of snow, not a lot. The air temperature is going to be whatever it is. And for the sake of demonstration here, we're going to call it below freezing, minus 10 degrees C. And we'll call it that point on our temperature axis of the graph. So now, if we graph temperature over distance, we get a slope that looks like that. So we're getting a lot of change of temperature over distance. Everybody with me? Anybody having problems here? If you do, just put it in the chat box and I'll try and explain it better. If people have had some science background, something similar, shouldn't be too hard to figure out. Everybody good out there? Okay. All right, now let's change one thing. Let's add more snow. Now we've added 150 centimeters of snow. Our ground is still the same temperature. Our air is still the same temperature. But when we graph it out, we end up with a different slope angle. We get less change of temperature over distance. Everybody good on that one? Okay, so whether we go to one type of process that we're going to delve into in a moment or another depends on the slope angle here as to how much change of temperature we get over distance. This is a very grossly simplified example. As I said, snow is a very good insulator. Storms come in at different temperatures. When that snow falls to the ground, we tend to have those temperature differences preserved. So we might get these variations within the snowpack. And if I'm out there doing temperature studies, I'll be putting thermometers in the snowpack and seeing how they change. But this here is our gross simplification, a big picture. So if everybody's got that, so when we get a lot of change of temperature over distance, we end up with a process that we call faceting. This has gone through a number of different words in the past, but the current one describes what the crystal looks like. And it's what we call a faceted crystal. Where we don't get a lot of change of temperature over distance, we go to a slightly different process that we call rounding. And those are the two processes that occur below the surface within the snowpack. So faceting. Faceting is a process where a crystal falls from the sky. Another concept here is falling from the sky. We have crystals. When they land on the ground, they start to disintegrate and they become a grain. Grains don't fall from the sky, crystals do. Grains develop on the ground. And this is a process that's promoted by cold air temperatures and a shallow snowpack. For those of you who are living in Mammoth at the moment, it's not been super cold this year, but we do have cold below freezing air temperatures at night, and we have a shallow snowpack. So consequently, a lot of our snowpack in the Mammoth area is becoming faceted, and we'll talk about that later. Faceting is a process where vapor moves through the snowpack and it crystallizes onto crystals. Let me see if I can make this work. And this here is a representation of the process. That grain changes. It ends up with growth lines on it. And it can eventually form a very cup-shaped hollow crystal. And it's the end result of this process here. And a crystal might look like this. They're pretty cool when you look at them under a hand lens. We don't have to go all the way to this end point here. We can stop over here with pointy little crystals. They're all faceted. Just depth hoar is an extreme form of faceting that forms at the bottom of the snowpack at depth. So let's get that concept there. There's a point a little bit further along where people get into confusion. Oftentimes it's referred to as sugar snow. A test for it is you can grab it, squeeze it, but it doesn't form a snowball. We look at it under a lens and there might be pointy little crystals right there. So we're interested in faceting because it can be a type of weak layer. Yep, we're going through it again. But that's the process there that we have. A faceted grain, again, might look like this, growth lines on it, depth hoar, the extreme type of it. We can get faceted grains at different places in the snowpack. Depth hoar at the bottom. We can also get what we call near surface faceting. It takes certain weather conditions to do this, but you guys might already have seen this. No, it's often referred to as loud powder. Some people call it recrystallized snow. They refer to it as the snow drying out. It isn't really drying out at all, it's changing. It's noisy when you ski through it. It skis like powder, but it isn't. It sounds kind of abrasive. And we'll sometimes get that near the surface. There's different places that we can get faceting within the snowpack, but we're not going to delve into that too much. All we want to know is faceting exists. Shallow snowpack, cold temperatures tend to promote it. It's a weak type of snow, which is why we're worried about it. And again, our test is to get it and squeeze it. When we look at it, it might look like coarse grained sugar. So that's faceting. The other type we get is what we call rounding. And again, we have our flake, it falls to the ground, it loses its arms, and it becomes a little grain. And this is promoted by warm air temperatures and a deep snowpack. And a rounded grain looks more rounded and it tends to stick to each other. And no bonds grow between the grains, such as maybe right here. And that's a process that is called sintering or necking. So the grains tend to stick to each other. Rounding will promote a more stable snowpack. Faceting will promote a more weak snowpack. And faceting is the predominant process we're getting at the moment because of colder temperatures, shallow snowpack. So, folks, good with that one, with that concept? We're not going to go any deeper into it there. Good. Any questions? No, put them in the chat box if you do. So, moving on, our faceted grains are often what we'll call a persistent grain. And it doesn't take, they can form relatively easily, but then it takes a long time for them to go away. So our facets are one type. Our extreme form of depth hoar, faceting is depth hoar. There's another type we'll talk about here, which is called surface hoar. And people might already have seen this. Surface hoar is kind of the frozen equivalent of winter dew. It forms at the surface and has little feathery crystals that grow up. They're very delicate. It takes, again, certain weather conditions to form these. We want clear nights, cold temperatures, no wind. We don't want sun because the sun will destroy them. And ideally what we'd like is a little source of moisture. We'll get these forming around lakes. We'll get the formed out of Mammoth up at San Joaquin Ridge. And some people might already have seen it. It's really pretty beautiful stuff growing at the surface. It only forms at the surface. First point, but it doesn't form within the snowpack. It's a result of those indirect weather effects. However, when we look at this one here, we can see that those surface hoar crystals have been buried deeper within the snowpack. Now we've got all these little crystals sticking up. Something happens to disturb them. They all fall over, they collapse, and that forms a very weak layer within the snowpack. Surface hoar is not a problem at the surface. If the sun comes out, melts it, no problem. The wind blows it away, no problem. Another storm comes in and buries it, then yes, we have a problem. But it's a weak layer that's persistent and it's buried below the snow surface. We don't have to deal with it too much in our environment here in the Sierra Nevada. Colorado, though, for example, has to deal with it a lot. And it's a particularly, let's call it, a treacherous form of snow once it's buried. The other thing to remember here is that surface hoar, when it's buried, does not turn into depth hoar. Depth hoar, as we talked about, is an extreme form of faceting that happens below the surface, generally at the base of the snowpack, because that's where we get the biggest changes in temperature. Surface hoar forms at the surface, is not a problem at the surface. When it's buried, it's a problem, and then it's called buried surface hoar. Everybody good on that one? That's always where people get confused because of this hoar word. Hoar is just kind of a generic word like pine tree. It can cover an awful lot of different things. So other views here of surface hoar. This is out in Nevada. It's really pretty beautiful stuff. Here we have some from the anthracite range out in Colorado, where we've got 1, 2, 3, 4 different generations of it growing. It's not often you're going to see that. Cool at the surface, a problem when it's buried, and a persistent weak layer because it forms readily, it goes away slowly. Some people who have been around longer might remember back in the early 2000s, there's a series of accidents in Canada. A number of kids were killed at Rogers Pass. There's a US Olympic snowboarder who died in the Selkirks. That was a result of a buried surface hoar layer. It had been buried, or had been formed about 6 weeks earlier. It was in the snowpack for 6 weeks. People knew it was there, people tracked it, but something happened to reactivate it and went through a cycle of that being a dangerous, persistent layer. And persistent just means it sticks around. So anything that's persistent should get our attention because, and we need to track it because being human, we tend to forget over time. Something's buried 2 feet, 3 feet down the snowpack. We tend to forget, and forgetting is what gets us in trouble. There's other types of persistent grains. This is called grappel or grapple, depending what country you're coming from. Let's see, Sven's been Googling hoarfrost. The Old English word hoary, meaning getting on in age. Are you implying something about me here, Sven? What's the deal?
No, that was. I just wanted to know what the word was. Every time I hear a new word, I always Google the etymology.
So, getting on in age. Well, no, we'll see about that. So here we've got grapple. It's another persistent grain. This is the snow equivalent of hail. It's little styrofoam balls. They fall from the sky, they get buried, they stick around a long time. We're worried about some of these persistent grain types because they lead to avalanches. And here in Switzerland, Canada, surface hoar, facets, and depth hoar tend to lead to the biggest number of avalanches. We don't have to worry in our environment in the Sierra Nevada too much about surface hoar. We do worry about facets. And we do worry about depth hoar, especially in the snowpack we've got now. So that's why we're thinking about these weak layers and what forms them. And again, it's weather and snow that leads to it. So faceting and rounding, they're just metamorphic processes. They can create or reduce the hazard. Just don't think we have to go in one direction. We can go from facets to rounding, back to facets to rounding. It all depends upon our snow depth and our overall temperatures. So they're not an end product, they're a product along the way. And eventually, everything goes back to water. So when we're out there, we're going to gather information about these three different categories: snow cover, layers, and bonding. We can get some of this before we head out, maybe from the avalanche report. We can do observations when we're out there. We can do formal ones. But for us, most of the time, we want to do informal ones. We're not going to constantly dig a snow pit every time we go out there. Snow pits are useful when there's gaps in our knowledge and information. So concept here is when you go out in the mountains, you can get more information by digging a snow pit, but if all you do is dig snow pits, you're only going to get 100 yards from the trailhead and not do what you want to. So it's when we want more information. So don't think you always have to dig into the snowpack. And that concept of digging into the snowpack all the time can be misleading. Snow pits give us some information, but we have to remember they're part of a very complex puzzle. They only give us a little mini snapshot of a big, huge picture. They tell us what is in that snow pit right there and then. It doesn't tell us about variability. We dig one at 7,000 feet, has no, on a north-facing slope, it has no correlation with one on a south-facing slope at 11,000. But human nature being what it is, we dig a pit, we do a test, and we get a score out of it, and our tendency is want to put all our faith in that score. We don't. We got to still go back to the big picture. But when we dig in there, we can look for that hard over soft layering. There's shortcuts to that, and we'll talk about that later. We can do a test and get a number. That's nice. We can do a bigger test, but this is a 2 meter by 1.5 meter block that we dig and then jump on. If all we do is dig these pits, we're not going to get very far. So oftentimes what we do is we step up our level of investigation, the less we know and the more information we feel we're missing. We might get a result like this, where a block just slides off on the top. And then we go, well, that's interesting. Then we have to go back again to the big picture. Are we seeing any evidence of this avalanching in real time, in real places? So the snow pit is a part of our picture, is not the end of everything at all. And too often people think that it's the end, that's all we've got to do. We don't. What a snow pit doesn't tell us about is variability. And as I said earlier, we've got a shallow snowpack at the moment, and it's variable. And it's variability that can trip us up. So we're always thinking about how things vary. This is a test that was done in Canada. The scores here are the way that we score a Rooch block, which was the big 2 by 1.5 meter that people jump on. A 2 means that it fails as you step onto it. A 6 means that it fails after repeated jumps. There. And as you might expect, 2 is sort of a poor indicator. 6 is something that we might feel happy about. This was due to a buried surface hoar layer in Canada, and Canada gets a lot of it. As I said, surface hoar is very variable in how it forms. So it was formed in these areas. It wasn't formed so much in these here. Could be a result of aspect to the sun. We can't really tell here. Now, obviously, it took an awful lot of work to dig all of these pits. So, there's probably a lot of undergraduates doing the digging. So, it's variable. If we dig a pit over here and we get a result of 6, we go, wow, no, I thought it'd be worse than that, but that looks pretty good to me. We dig it over here, 30, 40 yards to one side, and we go, oh my God, look at that. When we dig pits and get results, we're generally putting our faith in the low numbers that we get. We're not putting it in the high numbers. We're looking for reasons to turn us around, not reasons to keep on sucking us further ahead there. It's kind of a fuzzy concept here and takes a little bit to wrap your head around. So I think the key points are that we can dig pits, they provide valuable information, but it's very limited. We want to look at the big picture. We need to be aware of variability. And that's often what we call spatial variability. And that's where we can get into trouble. Most of the time, we're going to try and gather information informally. You know, how's the snow feel? Is it sticking to our skins? Oh, that sort of thing. Rather than digging a pit, we can go ahead and take our probe pole and push it in there and see what we feel. Do we feel hard over soft, soft over hard? This avoids us digging a pit in the snow, but gives us valuable information. Originally, snow was up to here. So the snow is slowly compacting. Grains are starting to stick to each other. So signs like this are indicators that the snowpack is stabilizing. On the other hand, something like this is off Minaret Road about 2 weeks ago, up out of Mammoth. Somebody put their ski pole in here and a crack went chunk all the way across and down here. That should get our attention right there. We've had a failure within the snowpack. It could be due to one of our persistent weak layers, like depth thaw, but this should get our attention. This is on what we call a little test slope, where it's pretty safe and no things are not going to go wrong because the road is flat right here, but it's an indicator of what's going on. This should get our attention. If we get on a slope and this happens, we've probably already stepped over the line and we're too far gone there. And all we can do then is figure out how we get out of this situation, and we should be heading home to change underwear after this point. This is not a good sign whatsoever when you're up on a slope. Shooting cracks, cracks that just run long distances, not a good sign here. We can go out and we can jump on these little windrolls. So we're going to go much more into the effect of wind as we go along, but we can just see, does this break off as a block? Is this one of our hard over a soft layer that we're interested in? As we travel, we can make a kick turn, and when we get into this area here, we can jump on it and see what happens. This is kind of a mini on-the-fly roots block. As I said, test slopes. We've got, we skied across here, somebody's gone above it, and they're just seeing what breaks off in this area. We can get into the snow, we can identify layers, we can ask ourselves, is this layer sticking to the one underneath it? We can try and pull down slope with our hands, see if it breaks off. As opposed to digging a snow pit, that might take us 15, 20 minutes or more, depending on how deep the snow is. We can do this in the upper layers in less than a minute and gain valuable information. We might have time to dig one snow pit in a day. To do these sort of tests, we can do 20 of them. Is the snow wet or dry? We've got a big roller ball here and pretty wet snow. I mean, that thing would probably take you out if it hit you. So we're asking ourselves these questions, and we're going to go ahead and have some red flags, things that should slap us over the head and go, wow, that's something to make note of. So a shallow snowpack, as I said, a shallow one is generally worse than a deep one. Most of the avalanches that we are concerned with happen in the top meter. So something less than 1.5 meters. Now, is it weak? Do we have a lot of facets in it? That's a weak snowpack. Is it variable over terrain? Do we have a strong over a weak layer? That would be a slab. Freezing. Snow doesn't like to be at about its melting point. So that's a bad sign there. Persistent grains. Do we have facets throughout the snowpack? Do we have depth thaw at the bottom? Do we have a buried surface thaw layer? And then we can also put in our test results. The compression test is where we load it from the top with our hand. 20 is thumping it 10 times up to 10. We do 10 with our fingers, 10 with our hand. So it fails then and breaks. A roots block 4 is when we jump on it once. And if we have failures in our test that are really smooth and clean as opposed to rough and irregular. So these are all things that when we're out there or before we go out, right now we can pull up the avalanche report and it says we've got a shallow snowpack and it's weak and it's variable. We can confirm that when we're out there. So we can get some of this before we head out. What's the temperature doing? If you're taking off clothing and are hot, then the snow is probably getting warm too. So that's all information that we can gain there about the snowpack. Okay, we've done a snowpack. Now let's go to weather and talk about weather side of things. We talked about how weather affects change right at the surface and how it can also indirectly affect those changes below the surface with temperature. So we talked about wind, temperature, rain, precipitation. All those things there. Wind is the big architect of avalanches. It's the biggest factor in what we have to consider. Wind moves snow from one place to another. It can completely remove it in one and deposit it all on the other side of the ridge or another place. Wind can move snow 10, 12 times the rate it'll fall from the sky. And it's very easy for us to underestimate how much the wind can move things around. When wind moves snow, it picks it up, it moves it to an area where it can be deposited, generally with less wind speed. As that wind speed drops, it tends to mechanically push one grain against another and mechanically bond those grains together. This is different to what we talked about with rounding, where there's more of a growth, a chemical growth that bonds one to another. With wind, we're talking about mechanical bonding. And that's what often, or that's what will lead us to what we'll call a wind slab, which is a layer of wind deposited snow where one grain is bonded to the other, but that layer is not bonded to what's underneath. There might be a weak layer or discontinuity between those two there. And that's our wind slab, is that wind mechanically bonded layer sitting on something weak, sitting on something hard. So precipitation. We get snow, we get rain. Now those will affect the surface. We've all been out there, people mentioned earlier, no rain being bad. It certainly is for the skiing. Rain adds heat to the snowpack. It also adds load. When it's buried, or actually when things are buried, we'll often end up with rain crusts. Sun, we'll get sun crusts. So what happens at the surface ends up getting buried again. Temperature, as I said, is different. Obviously we've got some temperature issues here. We'll have warm temperatures overnight. Snow doesn't like to be near its melting point. It goes ahead and loses strength. So we're keeping a track on that temperature. We can get temperature pretty readily before the trip. We can pull it up on the weather forecast of our favorite type. I tend to use National Weather Service there. People who haven't used it already can go ahead and pull up temperatures from Mammoth Ski Patrol. Just put a Mammoth Ski Patrol, it'll take you to this site. And it'll give current information at the bottom of the mountain at 8890, top of the mountain 11053, and mid-station as well. And you'll also get precipitation data for the last 24 hours. So that's a good place to just pull up immediate weather. If you go to the main Mammoth Mountain page, that's maintained by marketing. And as we know, Mammoth also always has 1 to 2 feet of packed powder, and it's always wonderful skiing. So go to Mammoth patrol site for accurate, good info there, and I use it all the time. It's valuable for giving us wind at low elevations, wind up at the Sierra Crest, top of the mountain. That's a forecast, but what's equally important is looking out the window. Now, has it snowed recently? How much has it snowed? No, this is what we'll call our out the window forecast. It's our nowcast. Now, is it windy? Has it been windy? Where's it moving the snow from to? What's our overall wind direction? As our big picture here in California, most of our storms come from the west and they intersect the Sierra Crest. The Sierra Crest doesn't run north-south. It runs north-west, southeast. So we're always thinking about wind direction, big picture and small picture. We have localized effects, and this is where the terrain will affect the direction and intensity of the wind. Looking here at some weather maps here taken from windy.com. This is low elevation at the surface here. And you can see our wind directions here. Little arrows moving all over. Kind of cool stuff, really. So that's our wind direction at the surface. Now here's our wind direction about 7,000 feet. These are all on the same day. There. Then, when we go all the way up here to 11 kilometers, pretty much all of our wind is coming from the west. It's unaffected by terrain. This is the overall pattern here. So wind is always going to vary with our elevation and with our terrain. So let's keep that in mind. Just because the forecast says west wind doesn't mean that's what we're going to see when we're actually out there skiing in terrain. Wind, as I said, is a big architect. It's going to move snow from from the leeward slope and put it on, it's going to move it from the windward slope, put it on the lee slope. We have cornices here. Cornices always form downwind. That where wind comes across, it forms a rotor here that goes ahead, deposits, and erodes snow. So in this case, our wind has been blowing right to left. We're always looking for wind direction. We're always thinking about it because wind direction is our key indicator as to where we find slab avalanches. Slab avalanches form again where one grain bonds to the next, and that happens in areas of reduced wind speed, where the wind is no longer in suspension, it's deposited. So wind slabs form in this area here. They don't form out over here. So we're going to use that fact to help evaluate terrain. Wind forms, or wind allows snow to deposit behind objects. Here we have some bushes. The wind speed slows and we get this little arrow of snow deposited behind. So in this case, it means the wind has been blowing right to left. So that's our indicator. So we're always looking for that to get our clues. And this might be different to what the forecast tells us. As I said, the wind will allow snow to be moved around and deposited at many times the rate that it falls from the sky. So looking at this photo here, where do you think the wind has been blowing from in this to create the cornice that we can see along the ridgeline? Type it on in for me. What have we got? Behind the ridge towards us from Ben. Yes, from behind. So yeah, back left, front right, something like that, yes. So it's coming sort of this direction, is forming the cornice. So based upon what we just talked about, where do you think we might end up with a wind slab problem on what we'll call the leeward slope? Type it on in there. What do you think? Yeah, you can do it. Come on through.
What's your question exactly?
Given that the wind is blowing from behind forward, we've talked about wind slabs forming on a lee slope downwind. Looking at our photo here, where do you think that has happened? We decided it was blowing from back forward. Where is down left from the center saddle? What else? What do you think? Just on the below the cornice on the visible, yeah, below the cornice, pretty well anywhere along here has that potential for the wind to be deposited. So anywhere here, there is a potential wind slab. So top of the ridge below the cornice, yep, all those. So keep that in mind as we keep going forward there. Wind is what we're always watching out for. And we'll expand that thought in a little bit. So when we're thinking about weather, things that get our attention, rain or dense snow, and so that adds load to the surface. How much of it are we getting? 2.5 centimeters an hour. Now about an inch or so an hour. An hour of that doesn't count for too much, but if we get it for 12 hours or more, then we are getting a foot within 12 hours. So that should get our attention. Wind, all it needs to do is move snow. We don't put a speed on it. Is it moving snow? Is it putting it on the slopes we're headed to? Or has it been putting it on there? Potentially a problem. And temperatures, again, around about freezing. Solar radiation. A little short burst of snow is not a big deal. However, strong radiation for long periods is a problem. So when we're out there, before we head out, those are things that should get our attention. And that's what we're trying to find. So that's some of our weather. Now, let's expand this into what we'll call snowpack climates. We've got 3 main ones: maritime, continental, and in between the two into mountain there. These are gross generalizations again. Maritime has a deep snowpack and warm temperatures. So what type of metamorphic process do you think we'll often get in a maritime environment? Thinking back to our 2 types of crystal, one with an F, one with a R. So what type do you think we'll get here? Grounded from windy, yes. So deep snowpack, warm temperatures, relatively uniform layers, avalanche danger quick to rise, often quick to fall. This is Mammoth, 2 years ago, I think it was. Okay, shallow snowpack, cold temperatures. What do you think we're going to get here? Type it on in. Faceting from Ben. Yes, correct. So this is the type of condition that we'll get in some of the mountain states. Montana, Wyoming, Colorado. This is where we get the faceting formed. And if you remember back to where avalanche deaths occurred in the US, that some of the mountain states got high numbers of deaths despite relatively low population. It's because of this here, where we get shallow snowpack, layering, and often a danger that's very slow to fall. The event comes in, the danger persists in those cold temperatures. And this is one reason why those mountain states tend to have more accidents. The storm comes in, it deposits some snow, it clears up. A day or so later, it's Bluebird Day, people are keen to get out, they forget about the danger. Intermountain is, such as the Wasatch, is likely to be a shallow snowpack early on, moderate to deep later. Might be variable layer, faceting early, rounding later. So again, these are gross big picture type definitions. Here on the Eastern Sierra side, on the east side, we'll have certain canyons that have more of a maritime aspect. Other canyons that might have more of an intermountain aspect. And there are definitions, no criteria that are applied. We don't need to concern ourselves with those. But the point here is, if you learn to ski, evaluate avalanches in California, be careful when you go to Colorado or Mountain State that you don't apply the same lessons from here to those areas, because you can get into trouble then if you're not careful. So that's our discussion of weather. So let's start to talk about terrain, the third arm of our triangle. Now, we can't control weather, avalanche activity, or the snowpack, but we can control where we go and how we do it. So one thing we want to do is recognize avalanche terrain so that we can avoid it when we need to. Here we're looking at the Sherwins at a Mammoth, as now I'm sure many of you guys are familiar with. Sherwins are a popular ski area out of Mammoth. They're close, they're accessible. This chute over here, that used to be heavily treed until President's Weekend of 1986, when we had big avalanche issues, big snowfall. I was working at Rock Creek at that time. We got 16 feet of snow over 4 days. So we got avalanches that took everything out down here, over here, a lot of things that are never run before ran during the storm. But the Sherwins are avalanche terrain, and we'll talk about that as we go along. When we're looking at avalanche terrain, we've got two critical observations that we're going to make. The first one's slope angle. The second is aspect. And that's primarily going to be aspect in relation to the wind, and we've already started talking about that. So these two factors are going to combine to give us significant avalanche problems. Slope angle. 30 to 45 degrees is kind of the prime slope angle. Below 30 degrees, it's generally too shallow to slide. Above 45 degrees, it's generally too steep to accumulate. However, you can still get avalanches in above 45 degree terrain. It's just often a smaller one is enough to have major consequence if it knocks you off in the wrong place. But 30 to 45 degrees is the main slope angle. For us as skiers, boarders, that's where we want to be a lot of the time. Now, an advanced ski run on Mammoth is probably going to be about 30 degrees overall. So we're going to go into those slope angles on a regular basis. But it's the slope angle that plays a large role in whether or not an avalanche will release. The lowest slope angle I know of is about 12 degrees for avalanches, which occurred in Japan, or one of the volcanoes where there's just basically so many people that it overwhelmed the cohesion of that slope. We can go ahead and evaluate slope angle through a number of different ways. We can use web-based tools such as CalTopo, HillMap, where we can go ahead and shade the different slope angles. And this is a good tool before we head out, and we'll talk about it. When we're out there, it's nice to have an inclinometer. Most people overestimate slope angle. A lot of people say that they ski for 50 degrees. 50 degrees is pretty damn steep when you're at the top of it, and not that many people really ski 50 on a consistent basis. It'd be nice to think that we did, but we don't. And a slope angle will keep you, meter will keep you honest. Looking at Mammoth Mountain, here are some of the slope angles on different runs there. So we're talking here about the start angle. That's where an avalanche will initiate. And that's our 30 to 45 degree range. They can certainly run over a lot less steep terrain. So the start angle, where it starts, the path is where it runs. Then we'll have the run out zone, which is where it stops. I mentioned that President's Weekend in '86. On that storm, the fracture lines up on Cornice Bowl were about 20 feet thick. Avalanches ran all the way down here to Sesame Street Chair 11, and they still had enough force to take out lift towers on Chair 11. And that's a long way from the start zone. And people who know that, terrain, have a visual of how far those avalanches run. It was an impressive year. That was the biggest storm I can think of, and certainly in my history. We've had bigger winters, but not that big single event. So the starting angle between 30 and 45 degrees is our first factor. We've already talked initially about aspect in relation to wind. Wind picks up the loose snow on the windward slope, it moves it downwind, deposits it on the lee slope over here. This is where we'll get our cornice formed, down here. So we're always looking for wind direction and signs of it, as we talked about. This is what we can call top loading or lee loading. We can also get over here wind blowing across the slope, and we'll end up with a series of windward, lee, windward, lee, windward, lee. And this is what we'll call cross loading, where it's blowing across. So when we look at this photo here, where do you think the wind's been blowing from here to create this pattern? Type it on into the box for me. Don't have too many choices. Left to right, getting from folks, yes. We also see there's a little bit of a cornice across there. That's another indicator for us. What else could help give this sort of a pattern, do you think? Another environmental factor that could give this. Aspect in relation to what? Sun, exactly. Yeah, so it could. But I think the little cornice here is our clue that it's wind. So we've got our little mini windward ones and our leeward. Okay, here we've got an area just outside ski area or slope. A charge has been put in there from the ski area. We get a fracture running around all this patch of snow. This is what we'll call a pillow of snow. So this is a wind slab that's been deposited in a lee slope. When we look at this one, where do you think the wind's been blowing from here? What direction? Type it on in for me. From behind, from windy. What else? Look for the little arrows of snow behind objects. What clue? That's your clue. What does it tell you for direction? Be bold. Left to right, we got from Andrew. Bottom up, no, okay, upper left to right. Okay, when we look here at these objects, we've got wind deposited behind them. See all these little ones here? So the wind has been blowing across this way. There might have been a component coming over the top, but primarily it's been blowing across the slope. So we have cross loading. That's created this lee area here of mechanically bonded grains one to another. That's formed a wind slab. That wind slab is now breaking as a result of that trigger, that charge being put in there. The problem we have as skiers and riders is, where do we want to ski and ride in this photo? Going to be right here. That's where most of the snow is. And there's a reason why that snow is there, because it's been deposited as a wind slab. We're not going to have a whole lot of fun skiing or riding out over here. So this is our catch, that often where we want to go to get the best snow is also where the highest danger potentially exists. So we'll expand on that as we go. But our clue here is deposition behind the object, cross-loading, potential wind slab in there, or actual in this case. All right, here we have Red Mountain between Thomas Place and Crowley Lake. Remember, wind can go ahead and blow in multiple directions. When we look at this photo here, it's been blowing in 2 directions. What do you think those directions are? Let's type that on in. Look for your clues, cornices, maybe where the wind has removed the snow. So Andrew's saying towards us and left to right. Yeah, we've got cornice up on the ridge here. These are fracture lines across here, but it's been blowing behind forward. It's also been blowing across. It's removed snow, deposited it, removed it, formed a cornice. So multiple different directions. So we keep that in our mind as we look for those clues. Again, the places we might want to ski or ride might be right in here, or in here, but that's where our maximum danger is. So we're keeping an eye out for that and ascertaining where the danger might be. Then we're going to decide if it's appropriate for us to go in there at that time. Similar here. These here look like the best places to ski and ride, but that might also be the highest danger. And we'll talk about that as we go along. A secondary aspect here, or a secondary factor, is aspect in relation to the sun. And sun is both a good thing and a bad thing. So it can go ahead and it can help get rid of those faceted crystals by increasing the temperature. So on a little bit of sun is a good thing, a lot is a bad thing. So some radiation coming in to warm those north-facing slopes up is good. Too much coming in on those south-facing slopes is a bad thing. Here we have solar input in the spring, and we've got a lot of these types of avalanches coming down all over, and that's the result of the sun hitting them. Here we have a lack of solar input during midwinter on, say, a north-facing slope. It allows those faceted crystals to persist. So sun is both good and bad, depending on our aspect, depending on our time of the year. So that's our aspect, and we'll use that to evaluate a slope. When we look at a slope, we're going to have, as I said, in relation to Mammoth, the starting zone, the track, and the run-out zone. This is a highway off Canada, and these little mounds at the bottom are to help dissipate the avalanche before it hits the highway here. So start up there. This is where we're concerned about our 30 to 45 degree range. Then we've got the path, which can be a lot lower. Then we've got the run-out zone or the deposition zone there. In this one, we can see that we've lost trees in the middle of the path, another indicator to us. This is what we'll call a well-defined avalanche path. There's just no trees at all. They've been cleaned out. Trees can give us other clues as well. This is what we'll call flagging. It's missing limbs on its uphill side. They've been torn off up to this height. It might be debris, tree debris in the snow. So that's all clues that avalanches run through these areas. So we're constantly evaluating the terrain. Also, as part of our terrain evaluation, it helps to have some knowledge of what's under the surface. There's a concept of anchoring. This is what helps hold the snow back in place. Now, a smooth slab like this is not going to hold the snow. Rough talus like this will, but we lose the relevance of this talus as it gets covered, and then it becomes a smooth slope. So anchoring, can be vegetation, it can be rocks. It's good to a certain extent, but after a certain snow depth, becomes less relevant. When we look at terrain as well, we're also thinking about what we'll call trigger points. And that's a physical characteristic of a slope that can help initiate or create an avalanche. And there's a few different ones out there. This is what we call convexity stress. The opposite is concavity stress. Rocks below the surface, trees, cornices can be a trigger point. So looking at these one by one, now rocks and shallow trees and shallow rocks, this sort of thing. Let's think about this a little bit here. We've got a deep snowpack, say over here, away from our rock. What type of snow formation do you think we might get? Below the surface, our indirect weather effect. What type of change do you think we'll get over here where the snowpack is deep? The F word or the R word? Which one? Type it on. The R word, yes. Okay, over here, our rock is effectively thinning the snowpack. So what type of snow formation might we get here? Where it's thinner. The F word, exactly. So is faceted snow weaker or stronger than rounded snow? Weaker, okay. So that's why the rocks can often act as a trigger point, because we get weak snow formed around that rock. Something like this. The rock over here could have been a trigger point. We can see how it's disrupting the snow, thinning it, and we might have got faceting there, and that became our trigger point. This avalanche initiated here, then it did what we call propagate, move out across the snow. So that's why we're often worried about trigger points and buried rocks. The problem is we can't see them. They're below the surface. So by the time we see this, it's too late. So another one of what we'll call our unknowns. We don't know what's below the surface. Things like this are often the reason that, say, 3 people might ski over here, the 4th one comes down here and hits that area of localized weakness and triggers something, even though other people have skied it before. And we see that not uncommonly. Convex rolls. The snow is under tension. Gravity is trying to pull it down slope. At the bottom of the dip, we have a compression where gravity is trying to push it together and the snow is resisting. With convexity stress, the snow is trying to get pulled down slope. It's under tension, it's under stress. We go in there and we can trigger an avalanche at that convexity rollover right here. We also have, as I said, the concavity at the bottom. That's where gravity's pushing it together. It's under stress, it's under load. We go in there and we can add additional stress, which then allows this portion to move down. So there's 2 areas of stress, depending on the terrain. And this leads us to a concept that we'll call remote triggering. Here we have 2 avalanches. Here we have ski tracks over here. Now, these weren't triggered by somebody skiing over this rise and triggering it right here. These were actually triggered from here, but they happened over there. And remote triggering is kind of a scary concept. We've talked about persistent weak layers. Let's imagine that we've got a whole bunch of little surface hoar layers sticking up here. We're skiing along, we'd add load on top, those layers underneath collapse. As they collapse, they go ahead and send out a whoomph sound, or actually they send out air, which leads to a whoomph sound. Some people might already have heard whoomping when you're out in the backcountry. It's not, should get your attention. It's not a fun thing. It's a layer collapsing. Along with that air and that whoomph, we get a shock wave that goes out. Let's say it goes out and it intersects that convexity stress right here. Then what we initiated here can occur here. And this is remote triggering. The same thing can happen at the bottom. If we're skiing here and that occurs there, it's not a problem. But let's say we're out down at the bottom of this slope. We go ahead, we collapse that layer, our woomph goes out, our shock wave goes up the slope, it intersects that weak layer. Now we've got terrain above us that's coming down into this area. So then that's a problem. Remote triggering is a real thing. It takes, again, specific instances and circumstances for it. But right now in the snowpack we've got out of the Mammoth area, we go ahead and, well, we are getting remote triggering and woomphing there. So let's keep that in mind as we go out. Looks like Natalie has a question here about what makes a tree or a rock a trigger point versus an anchor. Kind of a subtle line there, or a subtle thing. A lot of rocks together are probably going to be an anchor. Trees tend to be dots in the dotted line. And we often see avalanches going tree to tree. We think trees, give us an idea of safety. They're not. They actually give us a false sense of security. With avalanches, people often are hurt, damaged, or killed when they're taken into trees. People often think, well, there's a tree, I'll grab it if something happens. General rule of thumb is if we can go ahead or ski a ride through trees, then an avalanche can move through them as well. So Sven's saying no size and count, tells the surface roughness like sandpaper. Yeah, that's a pretty good explanation you've got there, Sven. It doesn't, yes, it doesn't allow for those anomalies in the snowpack. It's when we've got maybe a aberrant boulder sticking up a lot higher than the rest of them that can be a problem. But it is a subtle difference between those two. This is a little avalanche up in Alaska, backside of Mount Dickey. I was climbing here. We came up this direction here. I set foot up here. There's a woomph and something collapsed. A shock wave went out. It intersected some sort of stress here. And a couple of seconds after that woomph, this slab here slid off. If we've got a slab here, it means the wind's been blowing from behind forward. It's deposited snow in this area. We've probably got the same conditions right here. There's no reason why we don't. However, in this case, I felt justified in taking the rest of the group on up this slope. It was fairly small. The slope angle was less over here than it was there. There's a place out to our left where we could deposit people and go up at one at a time. Also, if you look here, there's a crevasse. If something falls off here, it goes into the crevasse. There's no crevasse here. And this is what we're going to talk about in a moment in terms of a terrain trap. So all of those factors allowed me to believe that it was safe to go up that slope and come back down. If any of those factors had been missing, it would have been a different story. So
Sorry.
I took the hazard, it existed here, but I felt we could mitigate it. This crevasse here is what we'll call a terrain trap. And it's a feature that exaggerates or increases the consequence if caught in that avalanche. So the crevasse was a terrain trap, gullies and drainages are terrain traps. Road cuts. The road cuts like that, we've got the road is like that, the cut is above it. Anything that comes off here will deposit within a small distance of our horizontal road. So we often think the road is safe because it's a road. It isn't. It's a terrain trap. Let's see, Sven is asking, what does a cross section of woomphing snow look like? It's probably going to be a firm layer, a weak layer. It could be facets, it could be buried surface hoar, then with something firmer above it. We're on the top, we disturb that layer there, it collapses, and let's say it keeps on collapsing all the way across that layer. That's when we get our woomph. So it's going to be a weak layer, probably sandwiched between two harder layers there. And expanding that concept a little bit here. I was going to use these later, but I'm getting hungry. Oreo cookie. This is effectively what we have there. And you're walking along on the top of the cookie here. You go ahead and you collapse this. whatever it is, this white stuff in here, imagine that white stuff's really loose there. You collapse it, and that's what causes that warm fingers that collapses and the air goes out. We're good. Cliffs. Just a little avalanche will take you off this cliff. This is climbing Rainier. It's a terrain trap. Creeks. Now you get taken and put into that. It's exaggerated the consequence. Trees and tree wells. As I said, if we can move through them, the avalanche can move through them, and they become a danger because they're an immovable object that we're likely to slam into. Cornices. We were talking about those earlier. Here somebody has stepped over that line here. This is where the cornice is going to break. They've gone over it and they realize their mistake and backed off. But by the time you get out on that side, if you add enough load, it's going to fall off. Every cornice falls off. So avoid them. Treat them with respect. So we're constantly asking ourselves, are we in the run out or are we not? No, we don't have to be in the start zone in that 30 to 45 degree range. We can be in the path below it. This here is Tobacco Flat, whoops, at a Convict Lake, just down the bottom there, south of Mammoth. Slope angle down the bottom here is pretty low. It's not much at all. However, this is what's above. This is on Little Morrison, or Mono Jim, it's also called. A couple of years ago, some guys went into Mammoth Mountaineering and talked to John there, asked him where it was a good place to go. He said, oh, stay down low in the trees. Avalanche hazard is high above tree line. One of them said, well, we don't want to happen today. What happened yesterday? Which obviously, you know, what happened yesterday? They came up this drainage here. They were on a 20-degree slope or less, and they decided we're not in that 30 to 45 degree danger zone. Therefore, we don't need to turn on our beacons. They came up, an avalanche came from above. I don't know if they remotely triggered or if it happened naturally. It buried one guy to his shoulders, another guy to his knees. The guy buried to his knees could get his shovel out and dig each other out. But they underestimated they were in the run out. How do you think they could have avoided this terrain trap at the bottom here? This is the big slope above them. This one there is, this one here. So how could they have avoided it? Fairly readily. Type it on and stay on the lower ridge. Yeah, just come out of the very bottom of the gully. That doesn't mean we're never going to go into these gullies. We are. We pick the time. Maybe we go in there, as we'll talk about later, one at a time. Maybe we don't travel up it because we're going slowly. We stay on this side, and then when we come down, we quickly ski through this section, pull out to the side out of the danger zone. So we utilize the terrain to our advantage. They didn't at all. So we're going to go ahead, and if when we need to, we'll avoid the terrain. In terms of our red flags, 30 to 45 degrees, wind loaded, we've got trigger points, terrain traps. So is it in the sun and baking? And do we have a weak slope configuration with lots of those little rollovers, convexities, concavities? Are there trees below or rocks below the surface, that sort of thing? So that's all more data we just put into the back of our brain. Now, by now, you're seeing there's an awful lot of stuff that we start to add up here. So that makes it complex. So that's our presentation there in terms of terrain.